Hello, today we're going to take a look at the limit of a function. So the first thing we're going to examine here is the notation itself. So this is what it's going to look like when you're finding a limit. Now, on your handout you may notice that the x, the arrow, and the a are sort of off to the side. It doesn't make a difference, it's just what software you're using, whether it puts it underneath or off to the side. It is more traditionally put underneath though, and that's what you'll see in almost all textbooks. Uh, so, to read this notation, what you're going to say is the limit of f of x as x approaches a equals L. Okay? So, what this means is that the value of f of x, the value of the function, it gets closer and closer to the value L as you choose x values that get closer and closer and closer to a. Okay, but they don't actually equal a. This is something that it's a very similar concept, and in fact, you'll come back to what you did last semester when you did the instantaneous rate of change. So anyway, the thing about limits is not all limits actually exist. So, for a limit to exist, the limiting value for the left side has to be equal to the limiting value for the right side. So what I mean by that is as you approach the value a from the left-hand side, it has to be equal to the same thing as you approach from the right. Okay, so you'll see it'll be more obvious when we do some examples in just a minute here. But the way you would write this then is that for a left-handed limit, so you're approaching from the negative side, your x value is getting closer to a from the left-hand side. Okay, you would write that as just like this here, and you can see the only difference is that there is a little negative, almost like an exponent for the a value. Okay, and so that means the left-sided limit. Okay. Similarly, we have the right-sided limit, or the right-hand limit, which means exactly the same thing except you're approaching from the right-hand side. And again, if you look up here, we've got a little exponent, only this time it's a positive because you're approaching from the positive side. Okay. So as we scroll down here. Okay, to have a two-sided limit, which you never actually call a two-sided limit, we just call it the actual limit. We just say the limit. You have to have that when you find this left-handed or this left-hand limit, okay, and you find the right-hand limit, if the two things are equal to each other, so in this case they both equal L, then the limit itself equals L, or the two-sided limit equals L. Okay. So, if the left and right limits don't equal, then it's just that the limit does not exist. Okay? So if you're a Mean Girls fan, you can get excited here. So what you need to know then is you need to know what the left-sided limit and the right-sided limit are actually equal to. Okay? In order to be able to calculate the limit. And as I say, that'll make a little bit more sense once I do some examples here. So I'm going to pop over to the camera here. We're going to take a look at these examples. Okay. So the first thing we're going to do is we're going to look at the limit as x approaches 2 of f of x. Now I've been given f of x here. It's this parabola here. So what I'm saying is so here's my x value of 2. Okay. And I want to say, as I approach 2 from the left side, what am I getting closer to on the y-axis? So as I get closer and closer to 2, I'm getting closer and closer to 6. Okay. And as I go from the other side, you can see I also come down and I get closer and closer to 6. So the limit itself is just 6. Okay? And in this particular case, f of a or f of 2 would just equal 6, and that's okay. Like that's sort of an easy one when you can actually just look at it and it actually just falls on the function itself. Okay, so a more challenging one here is if we've got this piecewise function. Okay, so g of x, if we have an x value that's less than 1, is going to equal x. Okay, so we can graph that here. Okay, graph that like that, and we'll have something like this. Okay, so you can see we go right up until that point. Oh, and I did that wrong because this should be an open circle because it does not actually include that point. So that should be an open circle. It's a little hard to see because I kind of made a mess of that. But as x is greater than 1 or equal to 1, it's going to be x plus 4. So we're going to start here, and this time it would be a closed circle. And we go up just the same. Okay. So you can see when I actually do the limit this time, as I pick x values approaching the 1 from the left-hand side, we're approaching y equals 1. Okay, so the left-handed limit would be 1. As I approach from the right-hand side, okay, I'm coming down this portion of the line, and you can see that it would equal 5. So because these two things don't equal the same value, this limit here, we just write does not exist, or DNE, we usually write. Okay. So, another one that can be, there's kind of an interesting case here, is if we look at this one here. Now I've given you the actual equation here, and if you think back to advanced functions, you can see that what we've done is you factor the top and cancel out the x minus 1s, and you'd just be left with x plus 1. However, you would have that restriction that x cannot equal 1. Okay, so we have this hole here. So we can't, if we look at that parabola there, we could have just subbed in, from part A, we could have just subbed in a 2 and found that the function equaled 6, and that would have been correct. But that's not going to work here because you can't sub the value 1 into the function because you'd be dividing by 0. Okay, so in this case, you just look, and it's not terribly difficult. As x approaches from the left side, okay, we get closer and closer to 2. As we approach from the right side, same idea, we come down the line and we get closer and closer to 2 again. Okay, and so even though that point is not included in the function itself, we are able to say that the limit is equal to 2 because the left-handed limit is 2, the right-handed limit is 2, so the limit overall is just 2. Okay. So we're going to take a look, and this is actually the exact same question here, but we're going to do the same thing using what we call the table of values strategy. And this may be, again, familiar from that instantaneous rate of change stuff you did in advanced functions. You may have done it this way. But anyway, all we're going to do here is you can look. So we've got the same equation, so we actually know what the answer is going to be ahead of time this time, but we're approaching 1. Okay, and so from the left you can see I started at 0, and I'm just going to get closer and closer and closer to 1. Okay. Similarly, then we're going to do it from the right. We're going to start at 2, and we're going to get closer and closer and closer to 1. And we could keep going, and we would get closer and closer to the answer, but the idea here is you're just kind of trying to find the trend. So if we plug in 0 into this equation, it will give you 1. Okay. If you then put in 0.5, it's going to give you 1.5, and you can calculate these on your own if you don't trust me, but I have done it ahead of time, so I do know that I'm right. If I sub in a 0.9, I'll get 1.9. 0.99 will give us 1.99, and 0.999 will give us 1.999. So you can see as our x value approaches 1, our y value, or our f of x, is approaching 2. So that's how you know our left-hand limit is 2. So if we do it from the right, we do the same thing, and if you sub in a 2, you're going to get 3. You put a 1.5 in, you're going to get 2.5. You're going to get 2.1 with 1.1. You're going to get 2.01 with 1.01. And you're going to get 2.001 for that last one. Okay. So again, our x value, we're now approaching from the other side. Before we were coming from 0 to 1. Now we're going from 2 to 1. Okay, so it's the right-hand limit. And you can see it is also approaching 2. So that's how we know that is equal to 2. Okay. So one that's quite a bit different, but this is one that will come up often, is ones like this, is we're going to do as x approaches 0 with 1 over x. So again, you can't sub in a 0 for x because you'd have 1 over 0, which is ridiculous. It doesn't exist. So we're going to do the same thing. We're going to pick these values approaching from the left, and then we're going to do it again approaching from the right. Okay. And again, I have done this ahead of time, so I know that my answers are right here, but so I'm just going to write them down quickly here. So if we put a negative 1 in, we get negative 1. We put a negative 0.5 in, you'll get a negative 2. We get a negative 10 for negative 0.1, a negative 100, and finally a negative 1,000. So it's not completely obvious here because we did stop at 1,000, but you can see it's getting bigger and bigger and bigger, and it's getting, quickly increasing. So the idea is from the left, it's actually approaching negative infinity is what it's doing. And the smaller and smaller you get, the closer and closer to 0, the closer it'll get to negative infinity. Okay. Similarly, if we approach it from the right, we would have positive 1, positive 2, positive 10, positive 100, and positive 1,000. Okay. And so you can see it's the exact same pattern. It's exactly the same, except it's now approaching positive infinity. And if you think about this, I'm sure you've graphed 1 over x lots of times, and it's going to give you this this shape like this, and you can see that this is exactly what's happening because you've got an asymptote on the y-axis, and so this is going up and approaching it's approaching infinity, while this one's approaching negative infinity on the left. And that's sort of what the point of a limit is that you can get as close as possible. But as you know, with an asymptote, we'll never actually reach infinity or negative infinity. So, all right. So these last ones we're going to do. These last ones we're going to use this method called direct substitution, and this is by far the easiest way to evaluate a limit. And it's just that if you look at it, x is approaching negative 2. Now you look, we've got an x on the bottom. There's no reason you can't divide by negative 2. Like, there is nothing about this that makes it so that we can't just sub the value directly in. So that's exactly what we're going to do. We're just going to say 8 minus, we're going to have negative 2 squared for negative 2. Okay. So by subbing in the negative 2 there, we're going to have 8 minus, that's going to be a positive 4 over negative 2. Which is going to give us negative 2. Okay. And when you use the direct substitution method, you don't actually have to do it from the left or the right, because there's no restriction at that point. There's nothing you need to do. Okay. And so we can do the exact same thing over on this one here. Okay. There's no reason we can't have a 0. If you look here, we'll have 2 minus, well, here, I'll write it out. When we're dealing with fractions, obviously we want to make sure we don't divide by 0. when we deal with square roots, we want to make sure we're not dealing with a negative number. But when we do this, you can see we're not having any of those problems. Okay, we get a positive 18 over a positive 2. So they're both positives. We don't have to worry about negatives. And of course, you've got a 2 on the bottom of the fraction, so we don't have to worry about dividing by 0. So we just get the square root of 9, which is 3. Okay, and that's all there is to it. I haven't thought of how to wrap up these videos yet, but thank you.